Hi, everyone. My name is Abhishek, and I'm a Part 2 student. First of all, thank you all for coming here and taking time out of your busy schedules to attend this talk. So this talk is about adaptive filters. So we'll explore 5 different things: digital filters, adaptive filters, and then 2 different main algorithms to implement adaptive filters. And then we'll look at some of the different applications of adaptive filters. So we'll start by looking at what a digital filter is. When I say adaptive filter, I mean a digital adaptive filter as opposed to an analog filter, which would sort of use components like resistors or capacitors. So a digital filter is, in the most basic sense, a component or an algorithm which takes a discrete time signal and sort of changes it in a certain way that we want it to change. For example, remove certain frequencies or remove certain amplitudes or enhance certain frequencies or amplitudes. So there are 2 main kinds of digital filters. And the first one is a finite impulse response filter. So here, if we look at the input sequence, that would be x of m. And our impulse response would be the set of coefficients that we call b, index m. So in this case, we can see that we have a finite number of coefficients, b of m. And that's why we call it a finite impulse response filter. And if we were to actually implement it as a circuit, this is the block diagram that we would implement. So Z inverse is actually a transform that causes a unit delay that allows us to multiply the coefficients with the previous values of x. So the second kind of digital filters that we have are infinite impulse response filters, where the set of coefficients can be practically infinite. And of course, this is a problem when you want to actually implement stuff. So one of the actual implementations of infinite impulse response filters is that you can use difference equations to sort of split it up into 2 different sections, as you can see here. So you have a finite set of 2 coefficients, but one set of coefficients is actually acting on the outputs y of n and sort of being fed back into the inputs to compute new values of y. And their main advantage over finite impulse response sequence filters is that they're efficient to, let's say you want some particular sort of behavior. You might need fewer coefficients in the implementation in an infinite impulse response filter as opposed to a finite impulse response filter. So this is something really important in digital signal processing. I don't know how many Part 1As there are here, and I don't know if you've come across this yet, but the Fourier transform is a transform that takes in as input a function in the time domain, let's call it g of t, and gives us a function g of f, which when takes a frequency, tells us the magnitude of that frequency within the time domain. So the output is in the frequency domain. It tells us how much of that signal has that particular frequency. Similarly, we can also have the inverse Fourier transform, which sort of just converts it back. So here's an example. Here we have 2 sine waves, one of 1 hertz and one of 2 hertz. And they're sort of superimposed with each other. And we can't really tell just by looking at it, obviously. So we apply the Fourier transform, and we get the results in the frequency domain. And we can see that we have a 2 hertz wave and a 1 hertz wave. And of course, we have 2 of each because you have the positive frequency and the negative frequency. And an example of what you might want, let's say, a fixed coefficient digital filter to do would be, let's say you want to get rid of the 1 hertz frequency. So an intuitive way of looking at it would be you'd be multiplying in the frequency domain this middle region by 0 and the outer regions by 1. So you get this output. And when you apply the inverse Fourier transform, you get a single sine wave of frequency 2 hertz. And this is sort of really good in terms of efficiency, but we can see a relation between time domain and frequency domain in terms of convolution. So convolution operation is an operation between two functions, which sort of, if you think of it this way, that in order to find the value at a particular point, you take the two functions and you flip one of the functions at that particular point, you multiply all the values and then add them up, and that gives you this output. So the reason I mentioned convolution is because convolution in the time domain equals multiplication in the frequency domain, and vice versa. So we can use this relation to actually derive different transformations in an intuitive way. For example, multiplying here by a square wave. You could think of it as convolving here with a square wave. So these are some of the common fixed coefficient digital filters that you might have, a low pass filter, a high pass filter, where you're restricting certain kinds of frequencies. And that can be done using the convolution theorem just by sort of applying operations within the frequency domain, as we saw before. But of course, there are some problems that fixed coefficient digital filters cannot solve. The first one is, let's say there's a time-varying noise frequency in your signal. And if we were actually to take the Fourier transform, let's say the 1 hertz is the noise. But the problem is the noise frequency is constantly changing. You don't know, you can't apply a static function and then use convolution, because the noise frequency is changing. You don't know what particular fixed function you need to use. Similarly, if the frequencies of the noise and the signal overlap, there's no intuitive way of what sort of function you need to multiply within the frequency domain to remove that noise. So this is where we start looking at adaptive digital filters. So the definition is that there are two main components to an adaptive filter. The first one is a digital filter, where the weight or the coefficients are adjustable. And the second part is an adaptive algorithm that tells you how you want to change those coefficients. So if we look at an adaptive filter in the context of noise canceling, we have two input signals. The first one is y of k, which contains our desired signal s of k. This is what we really want. And we also have n of k, which is the noise. So the k means that these are the signals at the kth sample. Another input, the second input that we have is x of k, which is not exactly the noise. It is, if it was just a noise, we could just subtract it straight away. It is a signal which is correlated with the noise in y of k in some way, and we hope that it's not correlated with the actual signal, because otherwise we'd end up canceling it out. So x of k, we use the correlation with the noise to produce an optimal estimate to the actual noise in the signal, and then we hope to subtract it. So this is the whole focus of noise-canceling adaptive filters, to find an optimal estimation to the noise in the signal. And we'll see how we do that. So first of all, we'll look at this theorem that says that in an adaptive filter, if we manage to minimize the total power output of the signal, we manage to maximize the signal-to-noise ratio, which is effectively what we want. So let's say that y of k is our signal, which contains our desired signal plus the noise. So we can expand. Yes, we can expand the actual signal, which is actually the desired signal plus the noise minus our estimate of the noise. So we square both the sides and then find the mean. And then this is the last term. And assuming, of course, that the actual signal, the desired signal, is uncorrelated with the noise, we can ignore that term because that zeroes out. And we are left with this. And here we can see that the mean of our desired signal is what it is. We cannot change it. However, what we're trying to do is we're trying to minimize the power output. And that can be done only by changing the power output of the noise. So if we manage to minimize this, that means we have maximized the power to signal ratio, the signal to noise ratio. And that is the main sort of concept behind all the adaptive filters that we look at in the noise canceling context. So the first adaptive algorithm that changes coefficients that we look at is the least mean squares algorithm. So first I'll define the Wiener filter, which is one of the most basic fundamental noise canceling filters. And every other noise canceling algorithm, almost all of them, are approximations to this filter. So let's say we have our estimate of the desired signal. In this case, I've called it error of k because it is effectively an error because we want to minimize it. It is not actually the error because this is our estimate of the final signal, but we want to minimize it, so we'll call it the error. So x of k is actually our input sequence, and this is once again correlated to the noise, but hopefully not to the actual desired signal. And here's what we're trying to do. We're trying to optimize these set of weights so that our estimate of the noise is in such a way that it minimizes the error. And in this case, we're looking at finite impulse response filters, so we have a finite set of weights. So we square the error and then find the mean, and this is what we get. So this is just some terminology into the literature if you actually want to do some research into it. So this is a really important figure. It shows that if we look at two dimensions of the weights, the first and the second weight, and we plot j, which is the mean of the square of the error, we see that in order to minimize the power, as we saw before, we want to minimize the power. In order to minimize the power, we need to get to the bottom of j, and that requires optimal values of weights. And if you have more than two weights, of course, you need to imagine the structure in more than two dimensions, but the idea is the same. And it's not necessary that your error performance surface looks like a circle. You might have more than one bumps, and some bumps might be deeper than others. So if we actually solve this equation by differentiating j and setting the gradient to 0, we get the optimal set of weights. And this is an analytical solution, and it gives us the least mean squared error if we're actually interested in minimizing that error. But of course, there are some problems with this analytical solution. First of all, it requires first-hand knowledge of R and P, but you only get that sort of knowledge as you're receiving the signal. And of course, it requires a matrix inversion, which can be quite expensive. That's why we look at approximations to finding this optimal solution. And so the first algorithm that we look at is the basic least mean squares algorithm, which is based on the steepest descent algorithm. Let's say we're at some point here on the error performance surface. So we find the gradient over here and sort of go in that direction, and we hope to sort of converge into the optimal solution. So one of the implementations of this algorithm is the Widrow-Hopf LMS algorithm. Here, for mu and the gradient, we use this, where E of k is the output from the previous iteration, and mu sort of determines your rate of convergence. And x of k is, once again, a vector that determines your signal that is correlated to the noise. So, of course, the main challenges with this algorithm are defining the appropriate values for mu, because if mu is too large, we'll be jumping around this structure all the time, but we won't actually converge. And if mu is too small, the convergence will be too small because we're slowly coming down that hill. But of course, there are other limitations of this algorithm as well. First of all, if the noise is not really stationary, the error performance surface can change quite rapidly from one iteration to another. And you might think, well, just increase mu, but then you're not really getting anywhere, as we saw before. So if the error performance surface changes too quickly, this algorithm isn't very useful. Secondly, if our estimate of the noise, which is somehow correlated to the noise, x of k, is proportional to the actual signal that we want, y of k, then it will actually end up canceling it out because we're finding the least mean squared, and that is not what we want. Secondly, bit precision. This is not really that much of a limitation. It's more of a fact that we need to consider, that the coefficients, the weights of the digital filter, should ideally be more precise in terms of bit precision than the values of x of k, because you'd rather be imprecise and correct than precise and wrong. But one of the main limitations of this algorithm is fluctuation. So we imagine we end up sort of converging towards the optimal weights. The problem is we never actually get there because the value of mu stays non-zero, and so do its coefficients. So that's why we look at some different algorithms, like the recursive least squares algorithm. But first, we look at some of the variations of the LMS algorithm. So there's the complex LMS algorithm where the numbers are complex, which can be useful for certain processors which can sort of fundamentally perform arithmetic operations on complex data. A second implementation is an efficient implementation. And this is actually what Matlab uses if you want to use the LMS algorithm. So it uses something called the fast Fourier transform, which part 1As might come across soon, if they haven't already. So this is actually an efficient version of the Fourier transform, of the discrete Fourier transform. So our second algorithm is the recursive least squares algorithm. So first we'll formulate the problem. What is it that we're trying to solve? So our error signal is the same as before, but in this time, we're not actually finding the mean. We're just trying to minimize the squares. So if we actually square it and differentiate error and set the gradient to 0, we get an analytical solution which looks something like this. And we can see that this is even worse than before in terms of matrix inversions and number of calculations that you have to do. And secondly, this is sort of similar to what you did during your A-levels or something else, where you had a graph and you had to plot a line of best fit which had the least square errors, distance from all the points. And that is exactly what this analytical solution tells you. But of course, computing it is hard and inefficient. So we look at an approximation of this. So the recursive least squares algorithm, which is this, obviously, we look at a recursive solution to this, which sort of uses exponential averaging. So in order to actually derive this, you'll have to go through a fair amount of maths, which cannot be fit in 20 minutes. So this is an exponential averaging solution, and this is our set of weights. Over every iteration, we refine our set of weights so that we can get a better approximation to the noise. So we use the previous set of weights and then add this. So E of k is the previous signal. As we're trying to minimize the signal, it makes sense that if the previous output is less, that means we have done something good. We have minimized, we have lowered the error, so we must change the weights by a lesser amount. And G of k sort of dictates the previous information. So gamma is actually called the forgetting factor. So when you're using least squares algorithm on a graph, you have to take into consideration every single point if you want to minimize everything. But in this case, we sort of give preference to the latest value because the noise signal is changing, and if you have actually sort of outputted some previous signal, you don't really care about the amount of error it had because, of course, you must change and adapt to new noises. So if gamma actually equals 1, then we have an exact solution to the least squares analytical solution, which we had over here. But that involves storing infinite amount of data, which is not feasible. So the main comparison against the LMS algorithm is that RLS has a rapid rate of convergence compared to LMS, because LMS, the rate of convergence is defined by mu, but in this case, we compute in order to actually lower the error. But R-less is fairly more computationally expensive in comparison to LMS. So it depends on your application, it depends on your signal. Now we look at some of the applications of adaptive filters. So the first one is one I actually have a demo for. So imagine we have our friend called Steve at microphone B, and we are in this room. So Steve is talking, and we can listen to him. So imagine this is a video conferencing environment. Video doesn't matter here. The point is that we have a loudspeaker, and Steve's voice might hit different parts of the room and go back into our microphone. And this is our noise, our voice. And what we don't want is Steve to hear his voice again when his voice sort of bounces from the rooms back to him. So I'll do a demo for this. Hopefully this should work.
Hello, this is Steve.
Hi, Steve. It's Jim.
Hello, Jim.
Did you get the year-to-date sales figures that I sent to you?
Yes, I did. Thank you. It looks like it's going to be another banner year for the department.
I know what you mean. We've been pretty pleased with how things have been going so far.
I need to get approval before I can release this information to the public.
Of course. Do you need anything else from my end?
No, what you've given me should be fine. I'll let you know how things go.
Sounds good. Thanks, Steve.
Bye.
Bye.
Right. I should have explained, this is the voice received in by microphone A. So, of course, microphone A doesn't want to hear Steve because we have heard Steve. We don't want Steve to hear himself back again. So in this case, we'll see a Matlab implementation of the fast LMS algorithm and see how that sort of works in order to remove Steve's voice from the input into the microphone. Remember, this is an adaptive algorithm.
Hello, this is Steve.
Hi, Steve. It's Jim.
Hello, Jim.
Did you get the year-to-date sales figures that I sent to you? I know what you mean. We've been pretty pleased with how things have been going so far.
So you can see Steve's voice has been canceled out. And
Of course.
over time, because
Do you need anything else from my end? Sounds good. Thanks, Steve. Bye.
So Steve's voice is being canceled out over time because this is an adaptive algorithm. The system learns what are the appropriate coefficients to cancel out Steve's voice. So if we look at this diagram, we can see that Steve's original voice is taken as an estimate into what might be the actual noise. And that, so Steve's actual voice signal acts as an estimate to the noise, our S of k. And then we find suitable weights to multiply with this input sequence over here. And we subtract that from the noise that is sent to Steve. So, as I mentioned, the value of mu, is quite important in terms of finding the appropriate rate of convergence. If it is too slow, the canceling will take far too long. And if it is too large, convergence will not occur. And we'll see an example of what happens if mu is far too large. So at the moment, mu was 0.025. Ideally, mu should be between 0 and 1. So we'll see what happens when mu is 0.2.
Hello, this is Steve.
Hi, Steve. It's Jim. Did you get the year-to-date sales figures that I sent to you? Things have been going so far. Of course. Do you need anything else from my end? Sounds good. Thanks, Steve. Bye.
So we see that Steve also almost becomes possessed. So, of course, the value of mu is quite important. And these sort of filters can also be used in mobile phones where you're using a loudspeaker. Look at another application of adaptive filters, and this one is called human encephalogram. So the idea is that you place different electrodes around the patient's head and near the face as well to measure the electrical activity of the brain in certain diseases like epilepsy or sleep disorders, coma or brain death. But one of the main problems that we face in this field is that when a user blinks or moves their eyes, the signal is far too strong to sort of let the user, let the doctor or DSP guy look at the actual brain activity. That's what I said. So if we look at this graph, so A is the actual activity measured from the eye. So this was measured using sensors near the eye, using these ones. So, and B is the actual encephalogram signal containing the noise, as you can see the large peaks. And you might think, well, these are periodic peaks. Why can't we just subtract a wave with a certain amplitude with a fixed frequency? Just use a fixed coefficient digital filter. But of course, not everyone blinks at the same frequency all the time. So that's why adaptive filters are used here. And if we actually subtract some factor of A from B, we get C, and this is the actual signal that we want, which can be used to diagnose certain diseases. So, so the ocular signals are actually, they act as our estimates of the noise, and we apply certain weights to them. These are the weights that we optimize, and we multiply them and subtract them from Y of K, which is, Y of K is B here. And we hope to get E of K, a corrected signal, which is C over here. Another application is fetal monitoring. So right before or during a woman giving birth, a doctor might want to analyze the condition of the baby. So they attach electrodes on the mother's chest to monitor heart rate, and similarly with the baby near the abdomen. But the problem is that the mother's cardiac pulse might affect the cardiac pulse of the baby. That's why they put the electrodes on the mother's chest. So that is the noise. Oops. So the heart rate of the mother is the actual noise, if we see over here. So D is the pulse from the mother's chest, which acts as our estimate of the noise. And E is our contaminated signal. This is what we measure from the abdomen. So it contains the pulse of the baby as well as the mother. But we only want to monitor the pulse of the baby. So we subtract a factor of D from E to get E. And from E, we can clearly see, well, to some extent, what the actual pulse of the baby is, and we can monitor different problems. Right. Question answers.